Hi guys, this is Dinesh from CSC section P, and I'm going to explain about semantic query expansion for smarter information retrieval using word embeddings. So, what is the key problem? Keyword based search. Traditional search relies on exact keyword matching, fails to capture meanings or context between the words. Example, doctor, physician. Doctor is not equal to physician in some keywords. We start by identifying the core limitations of modern search engines. Despite their sophistication, they are fundamentally keyword based. If a user searches for doctor, a document using the word physician might be ignored, even though it's semantically identical to user's thought. User searches. A document using the word physics might be ignored, even though it's semantically identical to the user's intent. This keyword-centric approach prevents systems from truly understanding what the user is looking for, resulting in missed highly relevant results. Why meaning matters. Words can have similar meanings but different spellings. Semantic relationships enable more accurate search results. Girl, understand intent, not just the text. What is semantic query expansion? Semantic query expansion is our solution. It shifts the focus from words were used to what were the user's meaning. The magic behind this is word embeddings. They aren't just IDs, they are text vectors in a continuous space where words with similar meanings like doctor and physician are mathematically closer. But by leveraging these semantic proximity, SQE dynamically adds synonyms or related concepts to your user's query before the search is executed, ensuring we find documents based on these meanings. Core search algorithms used in these are embedding based search, cosine similarity, and BM25. Uh, Embedding based search. Embedding results represents words as dense vector based on context. Measure similarity using cosine distance. Find semantically related words. Example: doctor, physician, or surgeon, etc. What is vector space model? It is a mathematical foundation for comparing vectors, where a smaller angle between a query vector and a document vector indicates high relevance. In general means that representing documents as vector in multidimensional space. High cosine value equal to high relevance. Probabilistic search, BM25. BM25 is excellent for traditional keyword matching, intelligent weighing terms frequency against term weight. Now, let's come to the role of NLP in semantic search. The role of NLP in SQE is that drives semantic search. It first cleans and standardizes the text, but more critically, it creates the word embeddings. The slide visualizes the system architecture. Notice the symmetry. Both the initial document and the incoming user query are passed through the same embedding generator. This ensures they are represented in the same vector space, making their comparison via cosine similarity mathematically sound and highly effective for the findings. What is it pipeline? User query, and first the user will ask the query. Next, the NLP is got processed, pre-processed, or processing has been done on the query. Embedding generator, similarity computation, and rank results. Combines multiple mathematical models for accuracy. The real world applications are e-commerce recommendations, healthcare, and medical research chatbots. Let's say, let us know about a numerical example. Let's say our query is doctor. But in document 1, which contains the exact word doctor, receives a high relevance score. Crucially, document 2, which contains the synonym physician, receives a score of 0. This visually and mathematically demonstrates the failure of the keyword matching. We missed a high relevant document based on the system did not understand the semantic relationship between a doctor and a physician. Now we can apply SQE, semantic query expansion. First, our word embedding model identifies physician as a strong semantic match to doctor. We dynamically add physician to the search query. Rerunning the cosine similarity calculation, both document 1 and document 2 now receive a high similar score. The system was successfully moved beyond exact lexical matching to retrieval information based on shared meaning, solving the missed results problem. Conclusion. Semantic search focus on meaning, not just words, enhances relevance and user satisfaction, leads to smarter human-like information retrieval. This is the working of the semantic expansion. Now, this is my code. Here, there are few documents which contains the word which are similar to doctor. Let's say doctor, physician, surgeon, nurses, and here we can see shoes. So first we train the model. through embeddings, tokenization, and training embeddings. Next, the TF-IDF vectorization is done in here. After that, this is just a helper function uh, for the algorithms. Next, this is baseline, which is we are finding the doctor without using the SQE. This is sematic this is with using the SQE. Next, we are comparing both the results before doing the SQE and after doing SQE. What are the results that we are getting? And this is for visualizing in graph. So before SQE, we can find doctor in only document one. But after doing the sematic query expansion, we can find doctor, this one in doc 3 as physician, doc 4 as surgeon, yeah, like that. With the similar meanings, we can find that. So semantic query expansion is very helpful for finding the real world exam. Thank you.